Hi, my name is Richard Wei. I work on natural language processing and machine learning at Apple on Siri, which has nothing to do with compilers. So I wasn't a compiler engineer, but the frustration that I had with the existing tools and infrastructures made me a compiler engineer. So today I'm going to talk, about DLVM. It's a compiler framework for deep learning DSLs. I started this project as a sort of a research project in the winter break of my last year of college, and then I turned that into a thesis advised by Vikram, Adve, and Schwartz. So let's get into it. So let's start by talking about deep learning. So cats are awesome, and then I want a machine learning classifier to classify this picture, the thing in the picture, as a cat. Then how are the deep learning models doing this? Well, if you look at the neural network, well, deep learning is all about neural networks. And then a neural network simply maps some input to some output. And then if I have a cat picture as an input, and then the output would be the representation of the word cat. You can also have other layers, like predicting the color of the cat, so you can have multiple outputs of this neural network. Okay, cool. So how is each neural network doing its job? So since this is a compiler conference, I want to introduce some nuts and bolts of machine learning here. So in each layer of this neural network, you have these connections from input to output, which is called the weight matrix. And then in each node here, you have a bias and a nonlinear activation function. So it's a simple math function. So you can represent this neural network, a single layer neural network, as fxw plus b. Sometimes it's wx, it doesn't really matter. So the terms for each, so each of these include prediction, activation function, input, weight, and bias. So weight and bias are the actual parameters we want to train for this neural network. So you can also have multiple layers. They can connect together, and we simply represent them as pure math equations. So how do we learn? Well, most of the time we do supervised learning. We simply provide a expected output and create a loss function to compute the loss from the actual prediction. And then we do gradient descent. It simply calculates the partial derivative of loss with respect to each parameter, and then it subtracts that gradient from each parameter. So this is called backpropagation. So to compute gradient, there are two ways. One way is called automatic differentiation. It simply reuses the chain rule of differentiation and reuses AST nodes along the way, along the same graph. So symbolic differentiation is pen and paper transformation, and then requires a lot of heavy common subexpression elimination. So this is not the common way that we use in deep learning. So we use automatic differentiation. And then this is how we compute the derivative of loss with respect to every single parameter. So it's a reverse mode automatic differentiation, the chain rule. So let's take a look at the graph. This is a computation graph, and then the interpretation approach is storing two values in each node, the forward value and the backward value. Forward value stores the result of evaluation, and the backward value stores the result of differentiation on that node. So we want to learn W and B from example inputs and outputs, and then the first thing we want to do is define a loss function, and then we have an augmented graph. And now what we want to do is to compute the loss, and then we call this the forward pass. And after computing the forward pass, we have the result of each node, and then we can compute a backward pass. So the backward pass computes the gradients, DL, DW, and DL, DB. And then all we have to do is the gradient descent. So it propagates that gradient back to each parameter. So that's all there's to it in the training and inference of neural networks. So how are the current existing tools helping us do the job? Well, we have two kinds of libraries. The first kind is a layer-oriented library. So things like Caffe. So you have a limited layer description language, you have hard-coded gradients per layer, and then you cannot easily define custom computation. And then the second kind is computation graph interpreter. So this is the kind of tools that we want to talk about. And a computation graph interpreter is just like Theano, TensorFlow, Torch, MXNet. They have one graph for everything, and then embedded DSL. They often provide embedded DSL in Python. And then each node stores the forward value and the backward result, just like what we showed in automatic differentiation. And then it launches one GPU kernel per each node, mostly. And then, so how are these toolkits providing a programming model? Well, so let me show you some code from TensorFlow. So this code is simply trying to do a matrix multiplication of x and w. And the second dimension of x is 200, and the first dimension of w is 100. And these two matrices simply don't match. So they are not compatible. So what happens is that runtime, you get this runtime error. And then, congratulations. So, well, what can happen is that with scripting tools, you can have a really complicated training script that runs for hours, and at the end, you get a runtime error, and everything fails just because of a type error, right? So, this is about scripting, and you can do even worse things with scripting. Let's look at this piece of code. So, this is actually a piece of production code I found online. It's a deep learning code, and you don't have to understand what it's doing. I don't understand it either. But look at this. Look at the string here. So it's GNU Octave code. Developers actually write this kind of code as a string in Python and try to evaluate it. So it's a fact that developers completely ignore safety, and then failures are super impenetrable. And then software engineering is completely gone in this field. Right? So there are also problems with automatic differentiation. So let's look at this graph. So this graph is simply computing wx plus b. And then if we compute the derivative of f with respect to w, it's x transpose times 1, and then dfdb is 1. Okay. But under the assumption of interpreted automatic differentiation, forward pass has to be run before the backward pass, which means that we have redundant computation because none of the values of the backward pass requires in each graph in this graph requires any value from the forward pass. And then sometimes it occupies large memory because values from the forward pass has to be preserved along the way until the backward pass is done. And then it's really hard to compute Hessian or higher order derivatives. It's possible, but it's really ad hoc. So graph optimizations don't apply to backward computation because it's usually interpreting the same graph forward and backward. So there are also problems with the backend. If you dig into the backend, you can see this boundary check for each element-wise GPU kernel here. But when you launch it with CUDA syntax, and then, okay, the boundary check is redundant when the product, the grid size and block size equal to count, right? So in the current toolkits, there's no way to optimize that out. Not only that's the case, you also have to pre-compile everything at install time. That includes every operator and every data type. So the existing toolkits like TensorFlow, PyTorch, and all the others are basically providing an unsafe API for developers, and they use differentiation by interpretation mostly, and they mostly have hard-coded GPU kernels, and then mostly CUDA only. And again, it's a lack of software engineering. So all of this are following the pattern of having a Python embedded DSL in the front, and then in the back end, you have graph implementation, algebra optimizer, interpreter, and a CUDA kernel inventory. Everything's intertwined, and some frameworks even implement automatic differentiation in Python. So okay, very cool. So as a machine learning engineer who really cares about quality software, this is really frustrating, right? So we had to rethink what neural network or deep learning systems really are. Well, we had to think, okay, neural networks are really just functions from input to output. And then most neural networks are basically math equations, math expressions, sometimes with control flow. So, hey, aren't these just programs? Yes, so neural networks are just programs. And then all these problems like intermediate graph representation, compute optimizations, automatic differentiation, these are all just a compiler problem. So we have a new compiler problem here. So we want to represent neural networks as functions without single graph restrictions. We'll stop calling them graphs. We'll call them functions. And then we use efficient automatic differentiation, and we can compute higher order differentiation very easily using compiler tools. And then we want cross-platform GPUs and machine learning accelerators, and we want lightweight installation. We don't want to pre-compile and install all the kernels on your device. And it should support just-in-time and ahead-of-time compilation. So for this, I spent my winter break of school and started to implement this thing called DLVM. So what is DLVM? DLVM is an intermediate representation for neural networks. It's a framework for building neural network DSLs, and it's an automatic backpropagator. It's a high-level optimizer, and it's an LLVM-based compiler targeting CPU and GPU. So a DLVM-based deep learning toolkit will have these benefits. So it has lightweight installation. There's no precompiled kernels at all. And then it can support multiple compute architectures, high performance, optimized for low memory devices, and bridging the gap between prototyping a production software. That's really important. So DLVM core is a core language of the system. It has all the common things like IR, analyses, transformations. And then on top of that, I built a DSL stack. So today we're going to talk about the DSL on the right-hand side, NNKit. So it's a stage DSL embedded in Swift. And on the bottom we have LLGen. It's an LLVM code generator, and DL runtime, which handles memory tracking and stuff. And on top of that, it has command line toolchain, like DLC, DLOpt, just like LLC, opt. Cool. So let's take a look at DLVM core. So it has an intermediate representation SSA form. It's perfect for handling control flow in AutoDiff. And it has basable arguments like Swift intermediate language. And it has a textual format and in-memory format, which means that you can use file check. Okay. So DLVM supports first-class tensor type. So you can represent vectors, matrices, and higher ranked tensors. And then the core IR has a high-level set of instructions. You have element-wise unary operators, binary operators, concatenation, transpose, convolution, matrix multiplication, and also a general-purpose instruction set. And then example IR looks like this. You can define the module name and struct, type alias, and then you can define a function like this. And this inference function simply computes xw plus b. And let's look at transformations. Transformations include differentiation and optimizations. So for automatic differentiation, we have this function on the left-hand side, and we want to compute the gradient with respect to every input. And then the automatic differentiation pass in DLVM transforms that into a adjoint function, which computes the gradients. And then This is called source code transformation in classical automatic differentiation literature. It's not using operator overloading, which is interpretation, and it gives us lots of opportunities for optimization. So you have forward pass and backward pass. So this enables optimizations like this. So when you have large memory from the forward pass, and then you can simply release it and recompute it when it's needed. So you don't have to carry it along the way. So this is called checkpointing for reverse mode automatic differentiation. And then you can apply things like algebra simplification or like linear algebra fusion, which fuses a bunch of matrix multiplication into one. And then compute kernel fusion when you have compatible kernels, no matter element-wise or non-element-wise, you can fuse them together as long as the shapes match. And then let's look at an example IR and example IR function and see how we can do automatic differentiation and basically how the transformations work. So to get the derivatives with respect to W and B, all we have to do is to declare a gradient function with respect to 1 and 2, arguments 1 and 2. And then when we run differentiation paths, it canonicalizes every gradient function declaration in an IR module. So I have an entry basic block, and then copy instructions from the forward pass, and then it generates a backward computation. Then it's done. And after that, we can have things to eliminate redundant computation. For example, we can run algebra simplification and decode elimination to optimize this out. Okay, so the compilation phases of DLVM starts from DLVM stage raw, the raw stage of the IR, which goes through analyses and verification, all the familiar things, and differentiation. And then differentiation turns that stage to optimizable, and then you can run a bunch of optimizations on both forward and backward computation. And then there's compute generation. It generates a compute IR, which is a low-level IR, and it goes through compute scheduling, and then LLGen generates LLVM IR, and then targets multiple heterogeneous parallel architectures using LLVM's backend. So LLVM here generates a library that you can link against. So basically, we're treating neural networks as programs. So how do we use the LLVM? Well, to use the LLVM, we have to build domain-specific languages for neural networks. So NNKit is an embedded DSL in Swift. So NNKit is a staged embedded DSL. It's type safe. It's really important. And it generates DLVM IR on the fly. So you have statically ranked tensors from scalars to 1D tensor, 2D tensor, 3D tensor, 4D tensor, and then type wrapper. So when you use a rep type, it simply wraps the tensor type or the underlying type to lift it as an AST node. And then you can have operator overloading to have things that help developers to build their computation. And then you have lambda abstraction, and then function application. So when you do script on actual data, JIT compilation happens, and then it JITs DLVM IR, and then JITs DLVM IR, and then compiles that to binary and launches it. So here's how you define and execute an inference function. So inference function is simply using the lambda abstraction in Swift and calculates xw plus b. And then you can simply call inference on foo.w and foo.v, and JIT compilation happens there. So it's a really prototypical DSL, but there are lots of things that we can do. So it has seamless JIT compilation. It supports dynamic tensor dimensionality by JITting. And then it's easy to precompile models to binary when shapes are known. To recap, deep learning system is just a compiler and language problem. And then in the front end, We can have an application IDE or DSL, layer DSL, math DSL. They can depend on, so higher level DSLs can depend on lower level DSLs. And then the backend is really just a compiler infrastructure. That's what a deep learning system should be. And DLVM is such a system. It's focused on performance and expressiveness of DSLs. And DSLs really enhance safety, reliability, and developer experience. So our final goal is to bring software engineering principles into machine learning systems. So here's DLVM, DSL stack, backend, and some command line toolchain. And so in the back, we have LLVM compiler targeting multiple heterogeneous parallel architectures, and CPU. So all of this is written entirely in Swift. It's really cool. So here's DLVM. If you're interested, you can take a look at dlvm.org. And then thank you very much. Questions?
Hi. So you had this intermediate representation and all the optimizations, or a lot of optimizations and analysis passes. Did you write them from scratch, or do you reuse them at some point? Or
From scratch.
all of them?
All of them. Well, some are unimplemented yet, but the infrastructure there for folks to implement it.
Cool.
Yeah.
Thank you.
No, it's largely unfinished. Yeah. So again, the infrastructure is there, and then filling in some bits of stuff there. Especially the backend. The backend is unfinished yet. Especially the low-level IR, the compute stage, and the scheduling stage. Thank you.